Here is a problem that almost every drone builder, robotics engineer, and IoT developer runs into, and almost nobody talks about openly. You spend weeks, sometimes months, designing and building something incredible: a custom drone, an autonomous robot, a field sensor network. And then you go to connect it wirelessly, and you realize the technology available to you simply was not designed for what you were trying to do. Let's break down exactly why that is, and why it has held back an entire generation of makers. When we talk about wireless connectivity for maker projects, there are really three categories of solutions available today, and each one has a fundamental problem. The first category is standard Bluetooth, the kind built into every smartphone, every Arduino module, every cheap breakout board you can order online. Modules like the HC05, HM10, or the Nordic NRF52 series. These are inexpensive, easy to use, and they get the job done inside your house. The maximum real-world range for a standard BLE module is somewhere between 80 and 100 meters under ideal conditions. In the field, with obstacles, interference, and a moving platform like a drone, you might get 30 to 50 meters before the connection starts dropping. For a ground-based robot or a bench project, that is fine. For anything airborne or deployed at distance, that is a hard wall, and there is no way to push past it with commodity hardware. The physics simply do not allow it.
The second category is Wi-Fi-based solutions. Things like ESP32 modules with onboard Wi-Fi or dedicated Wi-Fi video transmission systems. Wi-Fi gives you higher bandwidth than standard BLE, which is attractive, but Wi-Fi range is even worse than Bluetooth in practice, often 20 to 50 meters without directional antennas. And the moment you introduce range extension hardware, you add cost, weight, power draw, and complexity. Wi-Fi also requires either an access point or a hotspot, which means your system is dependent on infrastructure. Take it to a field, a mountain, a remote deployment site, and your Wi-Fi solution becomes a paperweight. The third category is where things get expensive: long-range radio systems. LoRa modules can reach kilometers, but at data rates measured in kilobits per second, not megabits. That is fine for sending a temperature reading once per minute. It is completely useless for drone telemetry, real-time sensor fusion, or robot control. Dedicated RC radio systems, things used in FPV, solve the range problem for pure control signals, but they are closed ecosystems. They do not speak Bluetooth, they do not integrate with your smartphone, they do not support two-way high-speed data. And once you start looking at professional long-range wireless hardware designed for industrial or military use, the prices jump from tens of dollars to thousands. We are talking systems that cost $5,000, $10,000, $20,000. Completely inaccessible to an independent developer or a small team. So what are makers actually doing today? They are compromising. They are accepting that their drone can only fly within 100 meters before they lose telemetry. They are designing their robots to stay close. They are running cables where wireless should work. They are hacking together multi-radio setups, one radio for control, one for data, adding weight and complexity and failure points. Or they are simply abandoning ambitious ideas because the connectivity layer does not exist at a price they can afford. And this is not a niche problem. This is the central bottleneck for an enormous number of hardware projects. Think about what becomes possible if you could reliably communicate over kilometers instead of meters. Drone swarms that coordinate autonomously across a wide area, agricultural robots that traverse large fields and report back in real time, search and rescue deployments where teams in different locations share data without cell towers, environmental sensor networks spread across dozens of square kilometers, off-grid communication systems for expeditions and disaster response. All of these applications exist in the imagination of thousands of builders, but the connectivity layer, at a price that an independent developer can actually afford, has simply not existed. There is another dimension to this problem that often goes unnoticed: the firmware development barrier. Even if a developer finds a capable radio module, configuring it for a specific application requires deep expertise in RF protocols, stack configuration, and embedded C programming. The learning curve alone can add months to a project timeline. This means the capability gap is not just about hardware specs, it is about accessibility. The tools have been locked behind both price barriers and knowledge barriers simultaneously. So, to summarize the core problem, makers need long-range, high-speed, Bluetooth-compatible wireless connectivity that integrates with real development tools, works without infrastructure, and costs what a maker can actually pay. That product has not existed, until now. This is the Multi-Nav Pro Plus BLE module from RFOXiA.
And what it does is simple to state, but genuinely unprecedented. It delivers up to 50 kilometers of Bluetooth range for $59 for a pair of modules. Let that sink in for a moment. 50 kilometers, Bluetooth, $59. Here is how it achieves what commodity modules cannot. The Multinav Pro Plus uses a high-gain RF front end with an external amplifier and an advanced low-noise receiver. The result is a link budget that commodity BLE hardware cannot touch. Ground to ground, you are looking at 5 kilometers, man to drone, 15 to 20 kilometers, and drone to drone, 2 modules in the air, beyond 50 kilometers, at 2 megabits per second. That is fast enough for real-time telemetry, sensor streaming, and robot control simultaneously. The core processor is an STM32WB07, which handles both the BLE stack and your user application in one chip. The module is compact at 57 by 47 millimeters, small enough for any drone frame or robot chassis. It includes an integrated high-gain chip antenna, an accurate RTC for time-sensitive applications, and 4 dedicated interfaces: GNSS, sensors, motor and battery management, and programming via SWD. The firmware barrier? Eliminated. The RFOXiA AI firmware builder lets you describe your application in plain language and generates production-ready, fully customizable firmware. What used to take months now takes hours. The module pairs directly with the RFOXiA Connect app on iOS and Android.
Live map view, real-time sensor display, PS5-style drone and robot control, and a BLE chat mode for completely internet-independent communication between users. No towers, no infrastructure, no subscription. It is FCC certified, open source, and it ships today. The connectivity limit is gone. What are you going to build?